This is lesson 5.5, double angle formulas. And these formulas in sections 4 and 5 are going to be used to not only do what we did in class, which was find exact values of angles using the known angles of a unit circle. I mean, that's kind of interesting. But what it's most often used for is to form new identities, and also used in simplifying identities. And these are the kinds of identities, the trig identities, that you're going to be working with that model real life situations, like finding apex angles of sound waves in speeds of airplanes, or finding something that is a sound wave that actually is modeled by a sinusoidal wave. So we're going to talk about, we talked about the sum and difference formulas. We talked about taking the cosine of an angle, u plus v, and then being able to write that out as a sum or difference formula, and then using that to simplify an equation. And so the double angle formulas, we're actually going to use the sum and difference formulas to derive them, and we'll do that on the next screen. Okay, this is a double angle formula. And where we've seen this before was when we were graphing. We knew that we could find the period of sine by taking 2 pi, which is the period of sine, and dividing that by 2. So the new period would be pi. So the sine of 2u would be all of the angles that are over a period of pi. So what we can do here is to derive the double angle formula. I'm just going to think of this, instead of being 2 times u, I'm going to think of it as being u plus u. 2u is just u plus u. And that's just the sum formula. So I would do the sine of u, the cosine of u, minus, our sine is the same sign, so that'll be plus, and then sine u, cosine u. Well, if you'll notice, we have a sine u, cosine u plus sine u, cosine u. That's just 2 sine u, cosine u. So the first one, the sine of a double angle, 2u, is going to be equal to 2 sine u, cosine u. So this part up here is the derivation, and then this is the actual identity. This is the part you need to have written down. Okay, we're going to use the same idea here to do the cosine. So I'm going to write it as the cosine of u plus u. So this is the sum formula. So I would do cosine u, and then it's the opposite sign, sine u, sine u. Okay, and so then that, if I tighten that up, that would be cosine squared u minus sine squared u. Now remember, that's not a Pythagorean identity. The Pythagorean identity would have a plus between it. So this one has a minus between it. So that's 1. Now, however, you can use the identity sine squared u plus cosine squared u equals 1 to write these in a little bit different form. For instance, I could substitute 1 minus sine squared u for the cosine squared, and this would be 1 minus 2 sine squared u. So this would be another formula that you could use. And then another time is I could substitute for the sine u. So I would have cosine squared u minus 1 minus cosine squared u. Substituting that for the sine squared gives me cosine squared u minus 1 plus cosine squared u. I have 2 of these, 2 cosine squared u minus 1. And so there's another one. So there are actually 3 formulas for cosine 2u. It is this red one right here, the blue one, and the black one. So if you're doing identities of any kind, you can substitute, or you can use any one of these 3. And then this shows how you found them. So we just started off with 2u. So the cosine of 2u is cosine squared u minus sine squared. or it is 1 minus 2 sine squared, or it is 2 cosine squared u minus 1. So all three of those identities are cosine 2u. All right, tangent is the same basic identity. So what we're going to do is we are going to write this as the tangent of u plus u, and then we will replace it with our sum formula. So this is going to be the tangent of u, 1 minus tangent u. The top is the same sign, the bottom is the opposite sign. So if you tighten this up, this will be 2 tangent u over 1 minus tangent squared u. And that's the equation. That's the formula for tangent 2u. It looks just like this. And u, remember, is just an angle. It's not magic, right? You could use theta here, you could use x there, but it still means an angle. So the tangent of a double angle. Okay, so here's an example on how you could use a double angle formula to solve an equation. We're going to be solving for x, and remember that x is an angle. X is an angle. So it's the same kind of problems we were doing in section 3 when we were actually solving for multiple angles. So what we have here is we have a double angle. Well, the sine of 2x is 2 sine x cosine x. And remember, we just derived this on the last screen. So all we're doing is substituting for the sine 2x. There was only one formula for sine 2x. You can look at your notes, look at that. Because I always get a question, they're like, where'd the cosine come from? Well, we just derived it. You can see where the cosine came from. All right, notice here I've got two terms. I'm going to factor a sine x out of both sides, both of them. So this leaves a 2 cosine x minus 1. And then I set each factor equal to 0. And so this is going to be the cosine of x is 1/2. Cosine is positive in the first and the fourth quadrant, right? So the angles in those two quadrants will be pi over 3 and 5 pi over 3. The sine of x is 0 at 0 and at pi. So my four answers are these right here. So the only thing we've added to solving equations is the double angle formula. That's all we've added, this right here. Okay, here's another type of problem that we'll be using, and it's basically the marriage between right triangle trig, so, ka, to, ah, and the double angle formulas. So the ratios are given on the triangle already. It's a right triangle, it's a Pythagorean triple, a 3-4-5, standard 3-4-5 triangle. And you're asked to use the figure to find the exact value of each trig function. So you need formulas and you need to know ratios. So the first thing we're going to do is find sine and cosine. Sine of theta is just going to be equal to the side opposite over the hypotenuse, or 3/5. The cosine of the angle is going to be the adjacent over hypotenuse, and that's 4/5. If I were doing tangent of theta, which isn't listed here, but the tangent of just the angle theta is opposite over adjacent, which is 3/4. That means anywhere I see tangent theta, I can replace it with 3/4. Anywhere I see sine theta, I can replace that whole thing with 3/5 because they are equal to each other. All right, so on the cosine of 2 theta, I have three possibilities. I have three formulas that I can use. One only has cosine in it, one only has sine in it, the other has both cosine and sine in it. So here I'm going to be dealing with fractions, so I think I just want one or the other. So my particular formula that I'm going to use here is 1 minus 2 sine squared theta. And so I'm going to rewrite this. I'm going to do 1 minus 2 sine squared theta here. So sine theta is going to be 3/5. So now when you figure the fraction, it's going to be 9/25 times 2. So it's going to be 1 minus 18/25. 1 is just 25 over 25. So the answer is 7/25. So the cosine of 2 theta is 7 over 25. Now, sine 2 theta only has one formula, and that is 2 sine theta cosine theta. So when I put the 2 there, the sine theta is 3/5. Now be careful again. Sine theta is 3/5. So you can replace all of sine theta. It's not the sine of 3/5. Please don't do that. Cosine theta is 4/5. This is 2 over 1, don't forget. So I have 2 times 6 times 4, so I have 24 over 25. So the sine of 2 theta is 24 over 25. Now, tangent. If I don't know tangent, I would know that this would be the tangent. The tangent formula is 2 tangent theta over 1 minus tangent squared theta. All right, so I know tangent theta is 3/4, so I would do 2 times 3/4 on the numerator, and the denominator would be 1 minus 9/16. Well, that leaves 6, 3/2 on the top, divided by 16 minus is 7/16. Flip and multiply, and I get 24 over 7. 24 over 7. Now, another way to think of tangent 2 theta is to take sine over cosine, sine 2 theta over cosine 2 theta. And so what you're saying here, let me write it down here, if I have the tangent of 2 theta, that's the same thing as the sine of 2 theta over cosine of 2 theta. The sine of 2 theta is 7/25. The cosine of 2 theta is what? Oh, no, wait, that was the cosine. Hold on. The sine of 2 theta is 24 over 25. And the cosine of 2 theta was 7/25. So flip and multiply, guess what? You get 24/7. You get the same thing as we did by using the formula. So if you know sine and cosine, you can just use that to find tangent. And so that's what we're going to do on the secant, cosecant, and cotangent. Secant is just 1 over cosine of 2 theta. Well, cosine of 2 theta is 7/25, so this is going to be 25 over 7. The cosecant is going to be 1 over sine, so it's going to be 25 over 24. And the cotangent is going to be 1 over tangent. So if tangent 2 theta is 24 over 7, then cotangent is going to be 7 over 24. And so that's how you do that. So we did like 8 of these problems using one triangle, using all of the relationships that we know between each one of these. Okay, here's a final type of problem that you could use to simplify. And so what you see here is you see 4 sine x cosine x, right here, 4 sine x cosine x, and that looks an awful lot like something like this. 2 sine x cosine x, remember, is sine 2x. So if I could find this, I could replace it with the sine of 2x. Well, it's pretty darn close because 2 times 2 is 4, and so this would actually be 2 sine 2x. So over here, this whole thing would be replaced with 2 sine 2x plus 1. And that's how that goes. All right, so that's all we have for today. Make sure you have a complete set of notes, and I will see you in class.